Lesson 9.4, Monitoring and Logging. Learning Objectives. By the end of this lesson, you'll have a production-grade observability stack running. Prometheus for metrics, Grafana for dashboards, Loki and the LK stack for centralized logs, and Jaeger for distributed tracing. This is a 60-minute advanced lesson, and it builds directly on the Kubernetes deployment you set up in Lesson 9.3. Observability isn't an afterthought in production ML systems. It's the difference between debugging a model issue in 5 minutes and spending 5 hours guessing. Monitoring stack overview. Before writing a single line of configuration, it's worth understanding what we're actually building and why the pieces are separated the way they are. Production observability breaks down into 3 distinct signal types. Metrics are numerical measurements over time. Request rates, GPU utilization, latency percentiles. Prometheus scrapes these in its own exposition format. Logs are discrete events, structured JSON records that capture what happened, when, and with what context. Loki ingests and indexes these. Traces follow a single request as it moves through your system, recording every function call and service hop along the way. Up and telemetry collects those and ships them to Jaeger. Each signal type answers a different question. Metrics tell you something is wrong. Logs tell you what happened. Traces tell you where it happened and why it was slow. Grafana sits on top of all 3, giving you a single pane of glass. Alert Manager watches Prometheus and fires notifications when thresholds are breached. That's the full picture. Now each piece will make sense as you configure it. Part 1. Prometheus Metrics. This Prometheus configuration is where you define what gets scraped, how often, and what to do with the results. The global section sets a 15-second scrape interval and evaluation interval. That's aggressive enough to catch a spike in latency or error rate within a single scrape cycle, important for a model API where a bad deployment can go sideways fast. The external labels attach cluster and environment tags to every metric, which becomes critical once you're shipping data to a remote storage backend or federating across clusters. The alerting block points Prometheus at your Alert Manager service. Without this, Prometheus evaluates your alert rules, but has nowhere to send the fired alerts. They just disappear silently. Each entry in scrape configs defines a job. The Kubernetes API server job uses role-based service discovery, meaning Prometheus automatically finds new endpoints as they appear in the cluster. No manual IP management. The ML Model API job does the same for your inference pods. The relabel layer config sections are doing real work here. They filter out endpoints you don't care about and rename labels to match your naming conventions, keeping your metric namespace clean. These alerting rules are the automated immune system for your Model API. Each rule is a PromQL expression that Prometheus evaluates on every cycle, and when the condition stays true for the specified duration, the alert fires. High error rate watches the ratio of 5xx responses to total requests. A threshold of 5% over 5 minutes is intentionally conservative. You want signal before users start noticing, not after. High latency fires when your P95 response time crosses 2 seconds. That's a user experience threshold, not just a system health threshold. The GPU alerts are particularly important for your dual P40 setup. Low GPU utilization below 30% means you're paying for compute you're not using, worth investigating whether batching is configured correctly. High GPU utilization above 95% means you're close to OOM territory, and inference will start queuing. Pod crash. Looping is one of the most valuable alerts in the set. A pod restarting more than twice in an hour almost always indicates an unhandled exception or an kill. Catching it early prevents a cascading failure. Every alert carries a severity label and a human-readable annotation, so whoever gets paged has immediate context without needing to open a runbook. Part 2. Grafana Dashboards. This JSON dashboard configuration gives Grafana everything it needs to render a complete picture of your Model API's health. The request per second panel is your heartbeat. A sudden drop to 0 means your service is down. A sudden spike might mean a traffic surge or a runaway client. Either way, you want to see it immediately. The latency percentiles panel plots P50, P95, and P99 on the same graph. The gap between P50 and P99 tells you whether slow requests are systemic or outliers. The error rate panel has a threshold annotation baked in, so the panel background changes color when you cross the alert boundary. GPU utilization and GPU memory panels are essential for your P40s. You want utilization in the 70 to 90% range during active inference. Below that, you're underbatching. Above 95% on memory, you're one large request away from an OOM kill. The cache hit rate panel validates your caching strategy. If it's below 50%, your cache keys are probably too specific or your TTL is too short. The dashboard refreshes every 10 seconds, which means you're always looking at near real-time state, fast enough to watch a deployment roll out and catch regressions as they happen. These target ranges and alert thresholds aren't arbitrary. They reflect what a healthy, well-utilized model API looks like in production. Request rate between 50 and 100 per second is your normal operating band. Below 10 suggests a routing problem or a dead service. Above 200 means you're likely approaching capacity and should be thinking about horizontal scaling. P95 latency below 500 milliseconds is the target. That's the threshold where inference feels responsive for interactive applications. The 2-second alert threshold gives you a buffer to investigate before users start complaining. GPU utilization between 70 and 90% is the sweet spot for your P40s. Below 30% is a waste of expensive hardware, and above 95% puts you at risk of memory pressure errors. The cache hit rate target of above 80% is achievable with well-designed cache keys. Below 50% is a signal to revisit your caching logic entirely. Zero pod restarts is the goal. More than 2 in an hour means something is actively broken and needs immediate attention. Part 3. Centralized logging. Loki takes a deliberately different approach to log storage compared to Elasticsearch. Rather than indexing the full content of every log line, Loki only indexes the labels. Things like namespace, pod name, and log level. The actual log content is stored compressed in chunks. This makes Loki dramatically cheaper to run at scale at the cost of full-text search performance. For structured JSON logs, it's an excellent trade-off. This configuration disables authentication, which is appropriate for a cluster internal deployment where network policies handle access control. The server listens on port 3100. The ingester settings control how log chunks are assembled in memory before being flushed to disk. The chunk retention period determines how long data stays in the ingester before compaction. The schema configuration is important to get right before you go to production, because changing it later requires a migration. This config uses BoltDB Shipper, which is Loki's recommended index storage for single-node deployments. The 14-day retention period means logs older than 2 weeks are automatically purged. Adjust this to match your compliance requirements. But remember that longer retention means more disk usage. Promtail is the agent that runs on each node, tails your pod log files, and ships them to Loki. Think of it as the log equivalent of a Prometheus scraper. It discovers targets automatically and handles the transport layer so your application code doesn't have to. The positions file is a small but critical detail. Promtail writes its current read position for each log file to this path. If the Promtail pod restarts, it reads this file and resumes from where it left off. No duplicate log entries, no gaps. The scrape config section uses Kubernetes service discovery to find Ps automatically. The pipeline stages are where the real processing happens. The JSON stage parses your structured log lines into fields. The label stage promotes specific fields, like log level, into Loki labeled dimensions, making them filterable in Grafana. The drop stage filters out debug level logs in production, which is important for keeping your ingestion volume and storage costs under control. The relabel/configs restrict collection to the ML production namespace and attach pod and container name as labels. This means in Grafana you can filter logs by pod name with a single click, invaluable when you're debugging a specific replica during an incident. Structured logging is what makes the difference between logs. You can actually query in logs you just scroll through hoping to spot something. This custom JSON formatter serializes every log entry as a JSON object rather than a plain string. The format method captures timestamp, level, logger name, and message as standard fields, but also extracts extra fields like request ID and user gerad when they're present. That request SWID is the thread that ties a log entry back to a specific trace in Jaeger. The two systems become far more powerful when they share identifiers. In the inference endpoint, notice the logging pattern. One entry when the request arrives, with the request ID and prompt length, and another when inference completes, with latency and token count. This gives you a complete picture of every request in your log stream without needing to correlate multiple events. The error handler logs the full exception alongside the request context, so when something fails in production, you have everything you need to reproduce it. No guessing, no asking the user to describe what they did. Part 4. Distributed tracing. Jaeger gives you the ability to follow a single request through every layer of your system and see exactly where time was spent. For a model API, that means you can distinguish between time spent in tokenization, time spent waiting for GPU compute, time spent in post-processing, and time spent in network XO, all in a single flame graph view. This deployment configuration runs Jaeger in all-in-one mode, which bundles the collector, query service, and UI into a single container. That's appropriate for development and moderate production loads. For high-volume production, you'd split these into separate deployments with a persistent backend like Cassandra or Elasticsearch. The port assignments matter. UDP port 6831 receives thrift-encoded spans from your application agents. That's the default Jaeger client protocol. Port 14268 accepts spans over HTTP, which is what OpenTelemetry uses. Port 16686 is the Jaeger UI. Once this deployment is running, you can port forward to that port and browse your traces in a browser. The service definition in the observability namespace makes Jaeger reachable by name from any pod in the cluster. OpenTelemetry is the vendor-neutral standard for instrumentation. By writing to the OpenTelemetry API, your code stays portable. You can swap Jaeger for Zipkin or a commercial APM tool without touching your application code. The tracer setup creates a Jaeger exporter pointed at your Jaeger collector service, wraps it in a batch span processor, which buffers spans in memory and flushes them in batches to reduce network overhead, and registers it as the global tracer provider. The fast API instrumenter call automatically wraps every route handler with a span, so you get request-level tracing for free. The manual spans inside the inference endpoint are where the real insight comes from. Each logical operation, cache lookup, tokenization, model generation, gets its own span with custom attributes attached. You're recording user ID, prompt length, token count, and whether the result came from cache. In Jaeger's UI, these appear as child spans nested under the parent request span, with timing bars showing exactly how long each step took. When a user reports that a specific request was slow, you pull up that request ID in Jaeger, and you can see in milliseconds whether the bottleneck was the cache miss, the tokenizer, or the model itself. Alerting with Alert Manager. Alert Manager is the routing layer between Prometheus firing an alert and the right person getting notified through the right channel. Without it, Prometheus just records that an alert fired. Nobody gets woken up. The global section configures your SMTP relay for email delivery. The routing tree is where the real logic lives. Alerts are grouped by name and cluster, which means multiple alerts from the same cluster fire as a single notification rather than flooding your inbox. The group wait and repeat interval settings control timing. Group wait delays the first notification slightly to allow related alerts to be batched together, and repeat interval prevents the same alert from paging you every 15 seconds when something is persistently broken. The severity-based routing is the key design decision here. Critical alerts, pod crash loops, error rates above 5%, route to pager duty, which means someone gets a phone call at 3 a.m. if necessary. Warnings are out to Slack, where the team sees them during business hours without being interrupted. Informational alerts go to email. This tiering prevents alert fatigue. If everything pages the on-call engineer, engineers start ignoring pages. The dynamic subject line in the email receiver includes the alert status and name, so you can triage from your inbox without opening the alert body. Observability checklist. Here's where you stand after completing this lesson. Prometheus is scraping all your endpoints on a 15-second interval. Grafana is displaying your key performance indicators with threshold-based color coding. Alert Manager is routing critical alerts to PagerDuty, warnings to Slack, and informational alerts to email. Loki is ingesting structured JSON logs from every pod in your ML production namespace with a 14-day retention window. Jaeger is collecting distributed traces with per operation spans and custom attributes. Your application is emitting structured logs with request IDs that correlate directly to those traces. And DCGM Exporter is giving you GPU-specific metrics, memory bandwidth, SM utilization, temperature, that generic node metrics simply can't provide. That's a complete observability stack. When something goes wrong in production, and it will, you'll have the metrics to know something is wrong, the logs to know what happened, and the traces to know exactly where and why. Next up is Lesson 9.5, where you'll close the loop with CI/CD pipelines that automatically validate and deploy changes to this production system. This production monitoring dashboard gives you a real-time health summary of your model API across 5 critical dimensions. The request rate panel in the top left shows traffic volume over time. A healthy system shows a relatively smooth curve. Sharp drops indicate a routing failure or a crashed pod, while sharp spikes may indicate a traffic surge or a misbehaving client sending retry storms. P95 latency in the top right is your user experience indicator. Values below 500 milliseconds mean your inference pipeline is running efficiently. When this climbs above 1 second, start checking GPU utilization and batch queue depth before assuming the model itself is the problem. GPU utilization in the bottom row tells you whether your hardware is earning its keep. For your P40s, the target band is 70 to 90% during active inference. Token throughput is a direct measure of inference efficiency. If this drops while GPU utilization stays high, you likely have a memory bandwidth bottleneck. The cache hit rate validates your caching strategy. Above 80% means the majority of repeated prompts are being served from cache, saving both latency and GPU cycles. This SLO dashboard answers a question that metrics dashboards alone can't. Are you actually meeting the commitments you made to your users? The SLO status bar chart on the left compares your current achievement against your defined targets across 4 dimensions: availability, P99 latency, error rate, and throughput. The blue bars represent your targets. The green bars show where you actually landed over the past 30 days. When a green bar falls short of its blue target, that's an SLO breach. And depending on your error budget policy, that may trigger a freeze on new deployments until reliability is restored. The latency percentiles graph on the right shows how P50, P95, and P99 latency evolved over the same 30-day window. The horizontal SLO limit line makes breaches immediately visible. Anytime the P99 line crosses above it, you exceeded your latency commitment for that period. Notice the spread between P50 and P99. A large gap means a small fraction of requests are experiencing dramatically worse performance than the median, which often points to occasional cache misses, garbage collection pauses, or GPU memory pressure on specific request sizes. These alerting rules define the 3-tier severity model that keeps your on-call rotation sane. Critical alerts demand immediate human attention. They represent conditions that are actively harming users or threatening system stability right now. An error rate above 5% for 5 minutes means roughly 1 in 20 requests is failing. A pod in a crash loop means a component is repeatedly dying and restarting. P99 latency at above 10 seconds for 3 minutes means your slowest users are essentially timing out. All of these route to PagerDuty and produce a phone call. Warning alerts indicate degradation that isn't yet user visible, but will be soon if left unaddressed. An error rate above 1% for 15 minutes, or GPU utilization above 90% for 10 minutes, warrants investigation during business hours. These go to Slack so the team has visibility without being interrupted outside working hours. Informational alerts, successful deployments, daily cost reports. Keep the team situationally aware without requiring any action. The discipline here is maintaining the integrity of these tiers. The moment critical alerts start firing for non-critical conditions, engineers begin ignoring them and the entire alerting system loses its value. This diagram traces the path a log entry takes from the moment your application writes it to the moment it appears in a Grafana dashboard or triggers an alert. Application logs, VLLM request logs, and Kubernetes system logs are all written to standard output on their respective pods. Promtail runs as a daemon set, one instance per node, and tails those log files from the host file system. It parses the JSON, applies label extraction and filtering through its pipeline stages, and ships the processed log streams to Loki over HTTP. Loki ingests the streams, compresses the log content, and writes it to object storage, S3 or Google Cloud Storage for long-term retention, with local disk as a write-ahead buffer. The index, which contains only the label metadata, stays small and fast to query. Grafana queries Loki using logql, the same query language you'd use to filter metrics in PromQL, but adapted for log streams. You can build log panels directly into your monitoring dashboards alongside your metrics panels. When a log pattern matches an alert rule, Alert Manager handles the notification routing, the same system that handles your Prometheus alerts. One alerting pipeline, two signal sources.